All right, so our next set of reactions are called aldol additions and aldol condensations. Um, these are kind of cool because they take place between ketones and ketones, or aldehydes and aldehydes. Um, so basically you're going to have a sample of aldehyde or ketone, and you're going to have um, the molecules sort of reacting with themselves, right? So if I'm sort of going to trace my carbons in my reactant and my carbons in my product, I have, or I guess I can do this. All right, one molecule, in this case aldehyde, is going to be playing the role of the nucleophile, and another aldehyde in that same sample, same aldehyde, same structure of aldehyde, is going to play the role of the electrophile. Okay, so this produces what's called an aldol. So let's just pick this apart. An aldol is an aldehyde and an alcohol, which I don't love that name because they don't have to be aldehydes. They can also be ketones. Whatever, I didn't make the rules. Bottom line of an aldol, the signature of an aldol is that you have an alcohol group located 1, 2, 3 carbons away from your carbonyl carbon. And that's actually, this is going to be the best possible way for you guys to sort of retrosynthesize. Let's say that I gave you this and I wanted to know what the starting aldehyde or ketone would be. What you're going to do is you're going to start numbering from the carbonyl carbon towards the alcohol, 1, 2, 3, and your new bond is always between carbons 2 and 3. Okay, so again, sort of color coding things as I had. This was my blue was my one molecule of this aldehyde. We're going to see that was the one playing the role of a nucleophile. The green was another molecule, that same aldehyde. That one was playing the role of the electrophile. The new bond that was formed is this guy here. Again, you can spot that by doing that numbering scheme. Always going to be between carbons 2 and 3. Okay, so let's see what happens here. These are going to be base-catalyzed reactions, which means that the main player is going to be that enolate ion. So the first step is formation of the enolate ion. So our base comes, reacts here. We have formation of our enolate, and the enolate, we have that alpha carbon that's nucleophilic. So then this is going to react with yet another molecule of aldehyde, because we know that, if this is our nucleophilic alpha carbon, we know that aldehydes and ketones also have electrophilic alpha carbonyl carbons, right? So that's exactly what these reactions are. Our nucleophilic alpha carbon is going to react with the electrophilic carbonyl carbon, and this is going to create one of those, world famous tetrahedral intermediates. Okay, what do we do when we get a tetrahedral intermediate? What do we ask ourselves? Is there a good leaving group? Is there a good leaving group here? No, because they're all carbons and hydrogens. So the only thing that can happen then is protonation of that alkoxide ion, and that gives us our aldol. And again, just to make a note, right, starting numbering from the carbonyl carbon 1, 2, 3, this bond right here is that newly formed bond. And I guess just to back up, I can color code things even a little bit more to hammer this home, right? Starting with our nucleophilic, the nucleophilic, it was a alpha carbon, but it was on one of these aldehydes. That would be those 2 carbons there. And we have this other aldehyde acting, I guess I can't use blue. This other aldehyde that was acting as the electrophile, those are those 2 carbons there. Okay, so here's a good example. Let's see if we can't work backwards and figure out what our aldol is. What are we going to do, or rather what our aldehyde that we started with was. What are we going to do with our aldol? This is our aldol. Note that our carbonyl group and the alcohol group are properly spaced. We're going to start numbering at the carbonyl carbon. 1, 2, 3. So that means that this bond here is the one I'm going to get rid of, or going to sort of erase to backtrack. And this carbon here used to be a carbonyl carbon. So my starting was an aldehyde, this aldehyde, butanal. Okay, so the retrosynthesis, the reason why I'm sort of hammering this home is because these reactions are kind of cool because they're taking place within just a sample of aldehyde or ketone. However, the products that you get are kind of messy. And so being able to do the retrosynthesis, figure out how, well, like what you started with is going to be really important. For aldehydes and ketone, for aldehydes, for the most part, the equilibrium actually will favor that aldol formation pretty heavily. If you have a ketone, it actually favors the reactants more. So you're going to have to do something special. If you were to distill out your product as it was formed or something like that in order to get an appreciable amount of product. Nonetheless, we're going to say that this happens for both aldehydes and ketones. You should know it's more favorable for aldehydes. But we're still going to be using them both. But again, this is why I don't really love the name aldol, because you can see that this right here would be an aldol that doesn't have an aldehyde group at all. Again, where's my new bond? Everybody take a second, see if you can't find it. I'm going to start numbering at the carbonyl carbon, 1, 2, 3. So this is my bond that should be erased. That was my newly formed bond. And again, the carbon at the base of that newly formed alcohol group used to be a carbonyl carbon. So this starting material would have been the cyclohexanone. Okay. Yeah, so we can go the reverse direction as well. Okay, so this is now starting off with an aldol. Should be able to do the reverse direction because again, this sort of equilibrium's readily, favors either side depending on whether you're talking about an aldehyde or a ketone. So we want to be able to move in both directions. How are we going to do that? We're first going to deprotonate that that alcohol, that hydroxyl group. That pair of electrons can come down and kick off that enolate ion. Normally not something we think about as a great leaving group, but because we're trying to move backwards, that's going to be the case. As well as, right, I mean, this is sort of resonance stabilized. That's the whole shtick about why that alpha hydrogen is relatively acidic. And then water will come and protonate that enolate. So this is just the mechanism for going in the reverse direction. Okay, so now the next thing, so that was an aldol addition. Aldols will then undergo another reaction called a condensation reaction. Okay, and so this is when if we just want to look, basically what's going to happen is we're going to get rid of this hydroxide group or hydroxyl group on the beta carbon, and there's going to be a double bond formed between that alpha and beta carbon. Okay, this can either be acid catalyzed or base catalyzed. So, just to note, I have my base and water will give me my aldol addition. Now, if I follow that up with heat, that'll catalyze the condensation. Okay, I think I left this, yes, okay. I left this reaction mechanism up to you guys because I want you guys to do this as part of your discussion. Again, one of the things that we're trying to really hammer home in this unit is y'all's proficiency with reaction mechanisms, making sure that you're making moves that sort of are legit and legal, okay? So anyways, when we have two aldehydes or ketones, the first thing that can happen is an aldol addition. If we then take that and apply heat, we will get a condensation. This yields what's called an alpha beta unsaturated aldehyde or ketone. Another way of saying this is an enone. The book loves to use the longer alpha beta unsaturated, right? Because this is the alpha, this is the beta. Again, also called an enone because you have that double bond, the ene, and the ketone or aldehyde, the one. So that's kind of the fancy name for it. Okay. What is this here? Yeah, I'm gonna make you do this mechanism. I guess it is in the notes. Just to note that since we're forming this alkene, we can either have two different stereochemistries, the E or the Z. You're going to get that trans product, or where the two big groups are on either side. Those are going to be the more thermodynamically favorable. So we won't really consider to get the minor amount of the cis product. There are some special examples where you don't even get any aldol formation at all. Basically, you don't need heat to get to the condensation step. And the main example that we're going to see of that is when that double bond is conjugated with a benzene ring, right? So notice that we're not going to stop at this aldol step because the condensation step, right? So this is the aldol addition step. This is the condensation step. We can't stop it at the addition step. It's going to proceed to the condensation step because what's going to form is a double bond that is now conjugated to this ring system here. So it's kind of a special example, but just note. Okay. Yeah, so we have these two different base catalyzed reactions with regard to our ketones or aldehydes. The first, it would be at lower temperatures, which would form the addition product. At higher temperatures, we have that condensation product. Okay. I mean, it is important to note, although it's important to note that the addition product isn't as favorable as the condensation product unless you're talking about aldehydes. But we're still going to do it for ketones. So it's not something I want everybody to have in their mind. Oh, you're not going to do additions with ketones. We're still going to see that. All right, so that was talking about reacting, a particular type of molecule, for example, butanal with itself. But what if we want a mixed aldol product, right? So what if we want to take this, this aldehyde over here? What if we want to take ethanal and propanal and react them with one another? The problem is that if we just toss some sodium hydroxide and water in here, you're going to get a mixture of 4 different products. You're going to have ethanol reacting with itself. And actually, this wouldn't be a bad idea for you guys to try to figure out what the products would be by yourself. I'm going to go through it kind of fast, right? The whole shtick being the alpha carbon on one of these molecules is reacting with the carbonyl carbon on the other one. You can have propanol reacting with itself. You can have propanol acting as the nucleophile and ethanol acting as the electrophile. Or vice versa, you can have ethanol reacting as acting as the nucleophile and propanol acting as the electrophile. Right, so if we just take a mixture of these two aldehydes, toss in some sodium hydroxide, we're going to get a real mess. So how do we do this if we want a particular product out of the two of them? Two different ways to do that. One of them is kind of it's a cheating way, and that is to start with an aldehyde or ketone that doesn't have any alpha hydrogens, right? So if we took formaldehyde and react that with propanol, we would get this sort of crossed aldol reaction, but it would be specific to propanol acting as the nucleophile, formaldehyde acting as the electrophile, because propanol is the only one that has any alpha hydrogens. So that's one way. However, I mean, that's only going to work in very special case scenarios, right? So the other thing that we can do, and this was the whole shtick about the LDA and the NaH we're going to see in sort of later on playing a similar role, is that we can use LDA, and that has the ability to convert 100% of an aldehyde or ketone into an enolate, right? So first we take one of those two aldehydes or ketones, treat it with LDA. We got a sample that's 100% enolate ion now. So then we can titrate in our aldehyde or whatever the second molecule is to get only one of our crossed product here, right? And again, This would be because this is acting as the nucleophile. That's our electrophile, forming our new bond located 1, 2, 3 between carbons 2 and 3. Okay, so bottom line is if you need to start with an aldehyde or ketone, like, you cut your aldol in half and there's 2 different aldehydes or ketones required, the trick is you're just going to treat one of them with LDA first, then mix them together. Another thing to look out for are these intramolecular aldol reactions, okay? Because here, notice that I have this alpha carbon. If I can turn that into an enolate ion and have it react, whoops, with itself, okay? This will give me, first, it would actually give me my, would give me my addition product. And then if I hit it with the heat, I would get my condensation product. Okay, so how do you know when this is going to occur? It's only going to occur if a 5 or 6 membered ring is formed, right? So although this was also an alpha carbon right here that has removable alpha hydrogens, if this enolate ion were to form, it couldn't really attack itself because that would form a 3-membered ring, which isn't terribly favorable. I guess to be good, let's bump this pair of electrons up. But you're only going to have this when your alpha carbon is located 5 or 6 carbons away from the other carbonyl carbon, right? So again, just to hammer this home, I have this alpha carbon located 1, 2, 3, 4, 5 carbons away from this carbonyl carbon. Then I have the potential to form an intramolecular aldol reaction. Okay, so just to summarize, when you have a sample of aldehyde or ketone and you add in sodium hydroxide and water, you'll get an aldol addition. We can tell using our little counting trick, starting with the carbonyl carbon, 1, 2, 3, that this was the new bond that was formed. And then if we hit this aldol with heat, we'll get a condensation reaction that then forms a double bond between that same 2 carbons, right? So again, this is still carbons 1, 2, and 3. If we want to do a crossed aldol addition or condensation, either A, we got to be lucky and one of our reactants doesn't have any alpha hydrogens, or B, we can do the whole LDA, treat one of them with LDA and then titrate in the other one. And lastly, we talked about intramolecular aldol additions and condensations. Remember, the key there is that you have your alpha carbon located 1, 2, 3, 4, 5, or 6 carbons away from a carbonyl carbon.